Okay, YouTube, in our last video, we looked at the behavior of the graph of y equals 1 over x, and we noticed a couple of things. First of all, that it has what we refer to as a vertical asymptote and also what we call a horizontal asymptote, values at which our graph approaches but never quite gets to. So vertical asymptotes, what we're going to focus on in this video is what we mean by a vertical asymptote. And we essentially mean that as our x values get really close to an x value for which our function is undefined. So at 0 here, remember 1 over 0 is undefined. As the x values we plug in get really close to that x value, our y values are either going to increase or decrease without bound. So essentially, what we're going to see here is the definition of a vertical asymptote. We say the line x equals a is a vertical asymptote of the graph of the function f if f increases or decreases without bound as our x values approach a. So you'll notice that there are 4 instances we give as an example here, but we say as x approaches a from the right side, as we come in from a to the right here, we say our y values are approaching positive infinity. So as our y values or our x values are getting really close to a, our y values are approaching positive infinity. Whereas if we approached a from the left this time, our y values might also approach positive infinity. Now it's possible that as we approach a from the right, our y values actually decrease without bound, or as we approach a from the left, that our y values decrease without bound. But it's one of these two always, okay? So in terms of vertical asymptotes, we say, well, where do they exist? Well, what I can tell you is that a vertical asymptote must exist where your function is undefined. So locating vertical asymptotes, it says if your rational function f, which is this polynomial over this polynomial p over q, is a rational function in which p and q have no common factors. That means that we've just simplified the top and the bottom. We say a is a 0 of q of x. In other words, if you plug a into this function here, you get 0 on the bottom. That would be bad. Then we would say x equals a is a vertical asymptote of the graph of f. So in other words, what we want to write right here is, and I'll type this here. This will look much better if I type it. Vertical That's a lot. Okay, so anyways, you might pause that and write that down because it's kind of an important fact. But basically, if you want to find the vertical asymptotes, it's always where the graph of your function is undefined. So what we're going to be doing is setting the denominator equal to 0 and solve for those x values. And yes, this is the same as finding the domain of the function. So it says here, find all vertical asymptotes if any of the graph of each of the rational functions here. And we'll go check it out on, maybe a graphing utility. But looking at this first one here, I'd say, well, this factors x over x plus 1, x minus 1. And so we'd say, well, what are the zeros of the denominator here? We'd say x equals plus or minus 1. So what I'm going to write here is actually this. I'm going to say vertical asymptotes at x equals 1 and x equals negative 1. Those two right there are vertical asymptotes. So when we go graph this, we had x over x squared minus 1. Let's take a look at this. We type in x divided by, in parentheses, x squared minus 1. We can see that this graph here, if I were to type in x equals 1, and x equals negative 1, and I know there are different colors here, you can see that this graph certainly does have 2 vertical asymptotes, where our y values, as we come close to those x values, either increase without bound or they decrease without bound, okay? So we would say our vertical asymptotes on this first graph are these right here. So now looking at the second equation, we would say, where are the vertical asymptotes? Now the interesting thing that happens here is when we factor this, maybe you already recognize this, we get x plus 1, x minus 1. The x minus 1s naturally cancel. And so what we get left with is this 1 over x plus 1. And what I want to do is I want to say that this right here, we would say our vertical asymptote, this would only ever be undefined. Well, I don't want to say undefined, but it's only ever going to have a vertical asymptote at negative 1. This is where our vertical asymptote will be, because that's the 0 of this denominator right here. Now on letter C, on part C here, take a look at this. We say the bottom doesn't factor. It just doesn't factor at all. So if I said, well, if that doesn't factor, we can still try to find where it equals 0. So set it equal to 0. Let's go solve this. And what I notice is that I'm going to get a negative on the right side, which means that I get imaginary results. In other words, I get I plus or minus I times square root of positive 1, which is just plus or minus I. The whole point here being this. We would say that this has no vertical asymptotes, but it has no vertical asymptotes only because the denominator doesn't have any real zeros, so no vertical asymptotes. So let's go take a look at these middle two graphs. By the way, I forgot to look at the graphs. We have x minus 1 over x squared minus 1 had a vertical asymptote at x equals negative 1. So we have x plus 1 divided by x squared minus 1. and I just want to check to see if I have this right here. It was x minus 1 over x squared minus 1. So here we go, and we said we had a horizontal, or sorry, excuse me, a vertical asymptote at x equals negative 1. So there that is. And then this other function over here, I think we had like an x plus 1 divided by x squared plus 1. Something like this here. Now, I probably have it wrong again. We say x minus 1. Yeah, I got to go change this, x minus 1. But we can see that this has no vertical asymptotes. I mean, this graph is always everywhere defined from left to right. So that's how you find vertical asymptotes. You just solve for the denominator zeros, or the zeros of the denominator. Cheers.